Finally, we'll discuss some results about the area of images and pre-images of sets under Lipschitz maps. Before discussing these results, we need a bit of notation. So given a function f from Rm to Rn, differentiable at a point x, the Jacobian of f, denoted Jf of x, is defined to be the product of the singular values of the matrix df of x. So if the dimension of the target space is at least the dimension of the domain space, then the Jacobian is actually equal to the root of the determinant of df transpose times df. If the dimension of the target space is at most that of the home space, then you can show that the product of the eigenvalues is similar. It's the root of the determinant of the derivative times derivative transpose. Now, if m is equal to n, then it ends up being that the Jacobian is actually equivalent to the absolute value of the determinant of f. So the area formula gives an exact formula for how measure is distorted under a Lipschitz map. So given a Lipschitz map from Rm to Rn, where the target space has dimension at least the dimension of the home space, for any Lebesgue measurable subset E of Rm, the integral of the Jacobian of f along the set E is equal to the integral with respect to m-dimensional Hausdorff measure along the image of E of the number of points in E that are also in the fiber or pre-image of Z under F. Okay, so that might look a little funny, but notice that if we had a injective function, so a function that was 1 to 1, then this would always just be equal to 1 here. And in that case, we would just get that the integral of the Jacobian of f on the set E is equivalent to the Hausdorff measure of f of E. And this gives us a precise formula for how measure is distorted. Now, in the case that we have a Lipschitz map going into a lower dimensional space, so in the case where we have a map going from Rn to Rm, where Rn is at least m, then for any Lebesgue measurable set, we have the following equality, that the integral of a Jacobian is equal to some dimensional constant, again, times the integral over the integral over f of E with respect to m-dimensional Hausdorff measure. But now instead of essentially counting measure or zero-dimensional measure of the fibers, we have the n minus n dimensional measure of the fibers. So the Coarea formula generalizes a little bit to more general sets. So instead of having a Lipschitz function f defined on a Euclidean space, there's a version of this theorem for Lipschitz maps defined on s-dimensional subsets of Euclidean space. So let's suppose that we have let's say we have m at most s at most n, and we have some set A in Euclidean space that is hs measurable. And suppose that we have a map, Lipschitz map f, defined on the set A. Then we have that the integral of the s minus m dimensional measure of the preimage of y intersected with A is at most the Hausdorff s dimensional measure of A. Now here, because we don't know that this function here is measurable, instead we use this upper integral, so integral star, which is defined to be the infimum over all integrals of g, where g is any measurable function that dominates the function f. So it's important to note that there isn't a reverse inequality here. So in particular, there's nothing close to having that this integral equals Hausdorff measure of A. Or in other words, there's no Fubini type theorem where we can recover the s-dimensional measure of A by integrating along a set of fibers, even when the function f is something simple like an orthogonal projection. So to give an example, let's suppose that we have the set that is the 1/3 Cantor set cross with itself. So this will have some dimension s strictly between 1 and 2. And let's let our function equal the orthogonal projection into the real line. So then notice this integral up here. When we take the Hausdorff s minus, so in this case m will equal 1. So over here we'll have 1 as well. So when we compute the s minus 1 dimensional Hausdorff measure of this fiber, notice that this fiber is non-empty only for points that are in the projection of this four-corner Cantor set. That is to say, only for points that are the preimage will be non-empty only for points in the image of the projection, which is exactly the Cantor set, which has Lebesgue measure 0, which implies that this integral here, as an integral with respect to one-dimensional Hausdorff measure, or Lebesgue measure, is going to be 0, because it's only positive on a measure 0 set. But since S is the dimension of the Cantor set cross itself, the Hausdorff S-dimensional measure of this set will be positive, and thus we don't have equality in this case. We record the following corollary of the previous theorem in the case that F was a projection into a subspace. So suppose we have integers m and n, and some number s in between those numbers. And suppose that we have a hs measurable set A, a finite s-dimensional measure. Then if we have a m-dimensional subspace V, then for almost every x inside the space V, if we look at the translation of the orthogonal complement by x intersected with the set A, then this will have finite s minus m dimensional measure. As a corollary of this, we can get bounds on dimensions of intersections with planes. So suppose, again, we have the same parameters m, s, and n, and now we have a Borel subset of Rn with dimension equal to s. Then, if V is some m-dimensional subspace, then we have that for almost every x inside V, the translate of the orthogonal complement of V by x intersected with A has dimension at most s minus m.